2020 ACI Concrete Solution Competition ESPOL. Variability of concrete setting time due to the mixture of retardants and plasticine admixture. The demand for concrete in Guayaquil is 40 to 21% of the national volume. Due to high temperatures, long travel journeys, and high performance expectation, concrete may require up to 6 admixtures. Volume of design according to the number of admixtures. In the volume of concrete produced in 2018, most of the mixture containing minimum 2 admixtures, but there are designs requiring up to 6 admixtures. Setting restriction, we will focus on the use of the following control variables. Current methods require up to 5 simulations to determine appropriate admixture dosage. The aim of this investigation is to generate a design tool that determines the setting time according to the dosage of plasticine and retardant admixture.
Hello everyone, my name is Brian Sersan. Continue with the presentation of this research. As a methodology, we first characterize the aggregate semen and admixtures to be used in this test. After that, we carry out 50 scenarios using a calorimetric test. We also analyze the result obtained and generate nomograms corresponding to each group of a scenario. Finally, we determine the decrease in the water footprint and the volume of waste generated in the laboratory. All the tests were based on the ASTM International and the ACI normative standard. We first generate a granulometric test, a calorimetric test, and a scenario design, a determination of the flow of hydraulic semen mortar, and a compressive strength test. This is the equipment we use. We use the M50 Hubat Lifer 6 horsepower mixer. And the scenario selection, there were some conditions. We applied the ACI 211 design method, and the dosage are summarized on this table. Some of those conditions has to be a flow to 200 to 300 millimeters over the glass disc, and not percent segregation and minimal exudation. For the compressive strength, we applied the ASTM C109, and we made 12 cubes were made to evaluate the result at 1, 3, 7, and 28 days. We cured them according to ASTM C511. As you can see on this picture, is the current time, the compressive strength test, and finally the result after 24 hours. As you can see in the picture, it was full deformed.
Results and analysis. Calorimetry curve. The temperature difference of the sample cell with the reference cell was plotted in order to be able to model with the last amount of systematic error that include change in room temperature. To smooth the curve, a regression was used that used the average of the previous, current, and subsequent values. The graphs is generated with these methods. The graphs allows us to see the directly proportional behavior between the head of hydratation and the semen content. Also, the graphs allows us to see how the setting time is delayed as the retardant increases. Additionally, it is observed how the head of hydratation increases slightly as the retarder is increased slightly reflect in the real setting time. The table quantifies this difference. Nomogram. Using a software, the nomogram were generated according to the semen content and its water-semen ratio. The graphs were organized with different tones according to the semen contents. Each line indicates a fixed dosage of plasticizer, while the x-axis defines the retarder. Finally, the initial setting on the y-axis is obtained in hours.
Adding to the results and analysis, we have the following nomograms. It is believed that while the retardant plasticizer, the initial set carryover. This test carryout is very sensitive to changes in temperature caused by mechanical failures, electrical outage, and laboratory use. Therefore, that certain scenarios have to be repeated to confirm the results. Two different water semen ratios were used for each test. For the first test ratio, it was 0.35, and the second one used is 0.45. Both used in 450 kilograms of semen per cubic meter. For the following two, the relationship used were the same, 0.35 and 0.45, but a variation was made in the amount of semen used that was 350 kilograms per cubic meter. The nomogram, which corresponds to 250 kilograms per cubic meter of semen and 0.45 water semen ratio, was not plotted because the mortar lake flow. The water-sand ratio of 0.55 had a performance slightly better, presenting a more cohesive and hydrated appearance homogeneously. However, the flows they were almost nil.
Parameters that influence the duration of concrete setting time. In these two graphs, we can observe the setting time according to the percentage of plasticizer and the content of cement in kilograms. Using small quantities of plasticizer implies shorter setting times, and using high quantities of cement results in shorter setting times as well. Results and analysis. Regarding compressive strength, the optimal cases were studied to be able to obtain the resistant design in 28 days using a specific content of cement and different combinations of retardant and plasticizer additives as shown in the graph. The water footprint in waste reduction volume could suffer a significant reduction using the nomogram. It is proven to be able to reduce up to 60% of the water consumption as seen in the table on the left, where for a critical case, using a conventional calculation method, 5 samples are required, and using a nomogram in the critical case, only 2 samples will be required. The same case occurs for the volume of waste, since the number of times that the test would be repeated in a critical case are reduced. So in conclusion, the reduction in the maximum number of cases needed to guarantee that the concrete satisfies with the design specification implies a reduction in the environmental impact caused by the industry in waste production and water footprint. Thank you for your attention and for the time given to listen to this presentation.